Okay, we're starting Unit 3 today, just Chapter 11, 12, and 13. This unit is a little bit different from what we've been doing. There's less calculations and computations and more explaining kind of how things are supposed to be done. Chapter 11 is about understanding randomness, and then also the big part of Chapter 11 is simulations. Chapter 12 will be surveys, and Chapter 13 is experiments. This is probably the unit I hear the most feedback from about how it's helped me out in college and psychology classes, biology classes. So this stuff really will make a difference probably if it sticks with you. So understanding randomness. If you're thinking of random numbers, all right, that's what our basis of this chapter is talking about, just using random numbers. Random numbers are just random numbers, just digits, like we would think. But we have two classifications. We have truly random numbers and we have pseudo-random numbers. So, on this page, all right, I'm going to have 4 numbers under this gray area, all right. I'm going to take the gray shade off, and you're going to pick a number. I'm going to put the gray shade back up so you don't overthink it. You're just picking a number. But we're going to talk about how random really human selection of digits really is. Okay, it really could be. So I'm going to take the shade off, you're going to pick a number, and then we'll put the shade back on. All right, ready? Here we go. Pick a number. All right, so that way you don't overthink it. So we would think that hopefully 25% of everybody would pick 1, 2, 3, or 4. If that was truly random, that's what would happen. Actually, if you pick 3, about 75% of people pick 3. 20% pick 2 or 4, and if you pick 1, only about 5% choose 1. So there's a subconscious link between picking numbers. So just having a human select number isn't always that great, all right? That's not actually truly random. So we have things that are pseudo-random. So pseudo-random values are generated in a fixed sequence, or they can be predicted. So pseudo-random values are generally computer-generated values. Your calculators have a random number generator, but it's based on a computer program. So if I wanted to, I could give you some directions, and then all of your calculators would start at the same number and would have the same sequence of numbers over and over and over again. And if you've never used your number generator on your calculator, which most of you haven't, when I show you that later this week, then you will have all the same number, okay? So they're not actually random. There's a fixed sequence. Truly random ways of getting random numbers are things you would think of like rolling a die, for example. That's truly random. You can't predict what's going to happen. Spinning a spinner. That's truly random. All right, there's also random number tables, which we'll talk about in a little bit. So pseudo-random is they're random, but really they can be predicted. Eventually the pattern's going to repeat, or your subconscious is going to pick a certain number. Then you have truly random, which is an actual random number. You can't predict what the outcome is going to be. So in this chapter, we're going to use this idea of random numbers, and we're going to be doing simulations. So we have some sort of scenario that's impractical to do physically, and we're going to use a simulation of random digits instead. All right? So we're going to be using random digits to show what would happen in a certain scenario. So all of these simulations are going to be based on some scenario. So here's a scenario we're going to be using right now. So suppose a cereal manufacturer puts pictures of famous athletes on cards and boxes of cereal in the hope of boosting sales. The manufacturer announces that 20% of the boxes contain a picture of Tiger Woods, 30% a picture of David Beckham, and the rest a picture of Serena Williams. You want all 3 pictures. How many boxes of cereal do you expect to have to buy in order to get the complete set? This would be impractical to do an actual experiment to figure this out. You'd have to go to the grocery store and keep buying boxes of cereal until you had all 3 cards. That might take 3 boxes, it might take 20 boxes, it might take 100 boxes. We don't know. So we can simulate this with numbers so we don't have to actually go out and buy any cereal. Now, When I go through this first example, it might not all make sense what we're doing at the time, but I think at the end it'll all come together. And then we'll do another example where everything comes together into one problem, and you won't be so confused at what's going on.
Volleyball players may report to the commons area at this time. All volleyball players report to the commons area.
So the question is, how many boxes do you expect to buy to get a complete card collection? So this would be nice if we can just simulate this once, but we want to know what happens typically. So maybe someone lucks out and it only takes them 3 boxes, and someone takes 25 boxes. So we need to find the typical number. So in a simulation, you're going to simulate buying cereal multiple times, not just once. And each one of those is called a trial. So we're going to do this multiple times. So here are all the steps, and they're all going to be written out. I'm going to use the same scenario, and then normally you won't have all these steps written out, but at least you kind of see what is going to be necessary to answer all these questions. So the first thing you're going to do is you have to set up your simulation. Just like an experiment in biology, you want to set up a simulation so that someone else could repeat it. So you want to have certain information so that everyone knows what is going on. So it says specify how to model a component outcome using equally likely random digits. So we're going to model the whole buying cereal process. So the first thing you want to do is identify the component to be repeated. A component is just a building block of each of your trials. So when we're talking about buying cereal boxes, and we were going to keep buying cereal boxes until we get all 3 of these athletes, a component in this case would just be 1 box of cereal. That's our building block. Each box of cereal is going to be important to us. Next, we're going to explain how you'll model the outcome. So that means you're going to assign random numbers. Now, this could be different for every scenario, okay? Some guidelines. Let's say we're rolling a die, and we want to assign numbers. Rolling a die, we might want to use numbers 1 through 6, okay? Let's say we're spinning a spinner with 5 sections that are all the same size. Well, then maybe we'll just assign every section number 1 through 5. So those aren't very complicated. A lot of the time, though, your information is given to you in percentages. So if it's given to you in percentages, then we generally want to base it off of numbers 0 through 9 or 0 through 99. So if you have multiples of 10%, you can use numbers 0 through 9. And then if you have 50%, well, that's 5 numbers, 0 through 9. If you have 40%, that's 4 numbers, all right? If you have percents that aren't based off of 10%, so like 65%, 25%, you don't have any decimals when doing random numbers, so then you could use numbers 0 through 99. I think this part might be confusing about where I'm getting this until you're going to see how all of this works. Since our problem, our scenario, is based on percentages, remember it says Tiger boxes were 20%, David Beckham 30%, and Serena Williams has to add up to 100%, so you get 50%. So we need to assign the numbers so that we can represent those cereal boxes in our simulation. So I will assign 0 and 1 to Tiger Woods cards in the cereal box. Right? Because it was 20% of the time. 20% of 10 numbers is 2 numbers. We're going to assign digits 2 through 4 to David Beckham boxes. And so 50%, the last 5 numbers, will be 5 through 9 to the Serena Williams boxes. Now I know that these numbers represent the same percentages I was given. 20% of the numbers are Tiger Woods boxes. 30% of the numbers are David Beckham boxes. 50% of the numbers given are Serena Williams boxes. You want to mimic your percentages given in the question. So we need to specify how to simulate the trials. So each trial should model what we're trying to accomplish. All right? And so you're going to go do that by looking at random digits. So we generally say we're going to generate random digits. If you're using a random number table, you'll look across a random number table. So we're going to generate random digits until you have a number representing each athlete. Right? The whole entire point of this problem is that we want to get one card of each athlete from the cereal boxes. So I'm going to have to keep doing digits until I have one of each. So at the very least it's going to be 3, but it could be 120. Just depends on the random numbers that are generated. And then you're going to state the response variable. And the response variable is just the question being asked. So we're asked how many boxes of cereal it would take to get these 3 cards. So the response variable is how many boxes of cereal it takes to get all 3 cards. Once you've stated all that, and generally it will be in paragraph form, you need to go back and run the actual simulation. So you set it all up, and then you're going to run the simulation. So you're going to run several trials. In this case, we're going to do 10, if we can. It says the more trials, the better. Okay? It would be nice if we could do 100, 1,000, 100,000 trials. And if you had a computer program, it could do that. If you're doing it by hand, you're normally going to do somewhere between 10 and 20 trials. The AP exam will give you a specific number of trials to do. That way, everyone has the same number on the rubric. So, we're going to make a chart. Normally that helps. And this list of random numbers is the list that was given in your textbook. All right? So when I make a chart, the first thing I want to have is the trial number. I got to keep track, that way I don't forget and I lose, and I have to do 30 trials and I only have to do 20. So 1, 2, 3, 4, 5, so on and so forth. Okay? Then I'm going to have the outcome. So in this case, it's going to be an abbreviated athlete name. So I'm going to keep track. Do I get 3 Serenas in a row and then David Beckham and a Tiger card? I'm going to keep track. And then what I'm really interested in is how many cereal boxes it really takes. So my last column is just going to be the number of cereal boxes. Because that's what I'm really concerned about. So we're going to look at these numbers, and we're going to start from the very end, and then we're going to go across. Okay? Remember, each one of these numbers is represented by an athlete. Is representing an athlete. So 0 and 1 are Tiger, 2 through 4 are David Beckham, and 5 through 9 are Serena. Okay? So, my first number is 8. Well, 8 represents Serena, so I'm going to write an S. My second number is 9. Well, that represents Serena, so I'm going to write an S. Remember, I'm going to keep going until I have all 3 cards. Well, then 0 is Tiger, so I'm going to put a T. And then 6 is Serena, so I'm going to put an S. And then 4 is David Beckham. Well, now I have 1 of each, so I can stop. So it's going to be 5 boxes that time. So that is 1 trial. Then you're going to pick up where you left off, and you're going to write out the outcomes. In this case, we want to do 10 trials. Since they only give us this 1 list of numbers, you'll stop if you write out. Generally, though, if it gives you 10 trials, you'll just keep going. You'll have another list of numbers, or you'll be using a calculator or something. So I'm going to try to do the rest of these pretty quickly, but you start at the 2, so it's David Beckham, and then Serena, and then David Beckham, and then Tiger. So that one only took 4, that's nice. And then the next one we have Serena, and David Beckham, and Serena, and Serena, and Serena, and then Tiger. So that took me 1, 2, 3, 4, 5, 6, 7 boxes. right? So then the next one, if you go in trials, I have David Beckham, Tiger, David Beckham, Tiger, Serena. That was nice. One took me 5. Then I go through the next group. So I have Serena, David Beckham, Serena, 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 David Beckham, Serena, 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 David Beckham, Serena, David Beckham, Serena, Tiger. That took a long time. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Then we keep going. So then trial 6, you have Tiger, Serena, 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 Tiger, David Beckham. So 1, 2, 3, 4, 5, 6. Then on to the next one. We just keep going. So Serena, Serena, David Beckham, Tiger. That takes 5. I keep going. Tiger, Tiger, David Beckham, Serena. That takes 4. So then the 9th one, we would have Tiger, David Beckham, Tiger, Tiger, Serena. So it took 6. And then if you look, we're going to run out of space. That's going to be a Serena, 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 David Beckham. So I won't actually get all 3. So we're going to go ahead and stop at 9 trials instead of finishing 10. So that's how you would go about doing your trials. After you've done the actual simulation, though, you need to talk about it. So it says collect, that's what we just did, and summarize the results of all the trials. So that means we're going to do descriptive statistic type things from the first unit. So put all of these numbers right here. So we're looking about the number of cereal boxes it took. Put them into your calculator and look at a box plot. Look at a histogram. Look at the mean and the median. Look at the shape. Look at the center. Look at the spread. You can talk about all of those things. We could also just talk about and answer the question. So if you do put it in your calculator, there is an outlier. 18 is definitely an outlier. If you do the test and all of that. But so if you have an outlier, maybe you don't want to talk about the mean, because remember outliers are affected by the mean. So you're talking about the median number of boxes it takes. So you use all your prior knowledge to make those decisions. And so the last step of this is to state your conclusion in the context of the question. So we were asking them about how many boxes it would take to get all 3 cards. So according to my simulation, it would take approximately 5 boxes of cereal to get all 3 athlete playing cards. The 5 is actually the median, so you probably want to say something about being the median somewhere. So I'm not just making up that measure. But so that's a simulation all the way through, from the beginning to the end. So you set it all up, you run the simulation, and then you make some sort of conclusion. Alright, this is the just checking, and it's just going to ask you to set up the problem, and we're actually going to not do the simulation on this one. So we're just going to do that part. So the Baseball World Series consists of up to 7 games. The first team to win 4 games wins the series. The first 2 are played at one team's home ballpark, the next 3 at the other team's park, and the final 2, if needed, are played back at the first park. Records over the past century show that there is a home field advantage. The home team has about a 55% chance of winning. Does the current system of alternating ballparks even out the home field advantage? How often will the team that begins at home win the series? So we're just going to set this up. What is the component? So our component is a building block here. So in this case, a component is one game. They win or they lose in one game. 2, how will you model each component from equally likely random digits? Alright, so we're going to assign digits. Notice there's a 55% chance of winning for the home team. So this is a 5%, so I can't use 0 through 9 because I can't use halves. So we're going to use numbers 00 through 99. I say 00 because if you're counting with double digits, you have to always do double digits. You look for 00, 01, 02, not 0, 1, 2, 3. You don't ever want to be looking at single digits and then double digits. You want to look at the same scale of digits all the way through. So I will assign 00 to 54 to the home team winning. And then 55 to 99 to the visiting team winning. Okay? And it's because it's based on 100%, so we have 100 numbers there. 3, how will you model a trial by combining components? So a trial will consist of generating random numbers, right? And so to think about what's happening here, we're thinking about how we want to see how often the home team wins the entire series. So we're going to generate numbers until the home team wins 4 times. Right? Because we're looking to see if they've won the series or not. So, 4 times. On number 4, what is the response variable? So we're looking at how often the home team wins the series. Right? And 5, how will you analyze the response variable? So this simulation is a little bit different. So we're going to be generating numbers and probably have like H for home and V for visiting. And then, actually up here I put until the home team wins 4 times. And it's until a team, right? It doesn't have to be the home team. So I'm going to have H's and V's, and whoever has 4 first is going to win. I'm probably going to keep track and say, okay, the home team won the series or the visiting team won the series. Okay? And so I'm going to keep track. And so at the end, I'm going to find the percent of the time the home team won. So that's going to be like the number of trials home wins the series divided by the number of total trials. Alright. Now we could do that simulation if we wanted to, but I'm just not, we don't have to, so I'm going to save some time. Alright, the last example we're going to go all the way through. Notice there's no prompts, there's no questions. We're going to be expected to do all of the pieces all by ourselves. Alright? So 57 students participated in a lottery for a particularly desirable dorm room. A triple with a fireplace and private bath in the tower. 20 of the participants were members of the same varsity team. When all 3 winners were members of the same team, the other students cried foul. Question: could an all-team outcome reasonably be expected to happen if everyone had a fair shot at the room? All right? We know that it could happen. You could draw 3 varsity players out of the lottery. But we're asking if it's reasonable. Does this seem like it's a fair shot? So we're going to do a simulation. So we're going to write out, the first thing we're going to do is write out paragraphs setting up our simulation, okay? So a component will be 1 student So my building block in this case is picking a student out of the lottery. So one student. Once I've assigned or told what the component is, I need to assign numbers for that component. Now notice there's 57 students, 20 on the varsity team, the rest of them are other students, so 57 total. It's not based on percentages, so I don't have to use 0 through 9 or 0 through 99. I just need to represent these 57 students equally. So, I will assign digits 00 through 19 to the varsity athletes, right? So if we're using double-digit numbers, then we're going to need to have 00. So I will assign digits 0 through 19 to the varsity athletes, and then 20 through 56 to all other students in the lottery. So I've defined my building block, my component, and I've talked about how I'm going to model those components with digits. So the next thing I need to talk about is what a trial is going to look like. So in the first example, we had to do numbers until we had all 3 athletes. So our trials could go on forever, really. They could keep going and going. In the last example, you can only do 7 numbers. You didn't have to do 7. You could do like 4. It's however many it took for the home team to win 4 times. But it was going to go up to 7. And in this case, our lottery is they're picking 3 students. So in our scenario, they're only picking 3 students, and they're always picking 3 students. So a trial will be the selection of 3 students. That's it. That's all you got to do. And then lastly, the response variable is whether the lottery is fair or not. Okay? So that's what we're looking for. It's all set up. So there were no prompts this time, but those are the 4 things you have to have. Component, how you're going to model the component, how you're going to simulate a trial, and what the response variable is. All right, so this time they don't give us random digits. So in the back of your book, on page A73, is this table of numbers. All right, you can see this table, and it has all of the digits in a nice little table of random digits, and we're going to use these for our simulation. That way everyone gets the same numbers. Okay. Now, we're using digits 00 through 56. That means you're always looking at 2 numbers. If it's a number that's outside of 56, then you skip over it. All right. They also have these spaces that are just trying to make sure you don't lose track of where you are. But if you are looking for 2 digits and your space is in the way, you need the last digit of the first column, the first digit of the second column, you can do that, put them together. Okay? So, we need to make a table so we can keep track of what's going on. We'll just do 10 trials. Okay, so we have trial 1, 2, 3, 4, 5, so on and so forth. We have the outcome. In this case, I'm going to have S for student. Remember that was 20 to 56. And V for varsity, which is 0 to 19. All right. And then I'm looking to see if all 3 varsity students are in the same room. So I'm going to put a yes or a no. Okay, in my last column, just to keep track. All right. The first one I'm just going to do on the table, and then I'm just going to go and look at the book while I'm doing this, and you can follow along in your table. But so for the first one, 96 is my first double-digit number. Well, that's outside of the numbers we're using, so we skip over it. The next number is 29, and 29 represents a student. The next number is 90, which is too big, so we're not going to use it. The next one's 71, and then 96, and 98, and 64. And the next number is 22, so 22 is a student. And then we have 06, so that's varsity, right? So that's what my first trial is. We had student, student, varsity. So no, that was not 3 varsity. So I'm going to continue in the same way. I'm looking at, again, page 873 so I can follow along. So 39 is my next number, so that's a student. And then 23, that's a student. And then 18, that's a varsity. Then 55 is a student. And 62 is too big, 82 too big, 69 too big, 92 too big, 91 too big. 41 is a student. And 25 is a student. So no, we don't have 3 varsity. Then I have 38, which is a student. 87 is too large, 29 is a student, and 41 is a student. Then I have 68, which is too large. That's the end of my first row. 68 was my last number. So it's my end of my first row. So then I just go and I start at the next row. Okay? So I have 71 and 62, and then 23 is a student, and 59 is too big, but 40 is a student, and 81 is too large, 80 is too big, 75, 92, 25. So 25 is a student. All right, then we keep going. We're going to do 10 of these. All right, so we have 18 varsity, 19 varsity, 20. So that is actually a student. So that didn't make it either. I was really close. We have 87, 10, 80, 77, 78, 43, 95, 69, 56. Then we have 38, 62, 80. So then third row, 3. 27, 24, 12, 30, 81, 73, 97, 47, 97, 70, 40, 61, 85, 64, 69, 27. Okay, so I did all of my trials. Alright, so now I need to draw some conclusions. So do I think this is fair or not? So according to my simulation, three varsity members only, didn't only, got the room 0% of the time. So although it is possible to draw 3 varsity players from the lottery, it seems highly unlikely. If you look at that example in the book, they actually use different random numbers, and they end up getting one trial that has 3 varsity players, so they get 10% of the time, but still it seems unlikely. Here it seems very unlikely. This is where it would be nice to have more than 10 trials, so you wouldn't have to do it all by hand, but you could have a better idea what's going on instead of just 10 trials simulated. So that is simulations in a nutshell. And we're going to spend the next few days just doing example after example after example because they're all a little bit different. Some of them, the numbers that you assign are a little bit weird, or sometimes what the component is seems weird. Sometimes when you run the trial, it's a little bit different from the last one. So they're all a little bit different. So we just do lots of practice.